So I was asked to give you a lecture on truss structures. You know what truss structures are? Truss structures. Bridges. Well, you are a mechanic aerospace, are you? Bridges. So, truss structures. Do you have good recording device? Will catch my accent? No. Because you should have talked to me 15 minutes ago, not 5 minutes ago. But for the good of our class, I'm going to sacrifice and do it, right? Otherwise, I'll just, and the weather is not good. That's why I say, guys, free day, right? Successful lecture. Okay. We might meet in 202, engineering 202, now it's 2020, you know, the spring. Someone intend to take that course in the spring? So I'll be your professor. So that when you guys are going to realize who I am. Right? So before I teach about truss structure, I should tell you that at Cornell in engineering, many people do research and teaching. And research helps to teach better because it exposes you to real problems, right? So you solve problems that are for real. Otherwise, we just read some books published by others, unless we publish our own book, and we teach you something that at sometimes is not as in depth as would be if you connect that with research. My research is not in truss structure, is in structures particularly, and I do research on composite materials. You know what composite materials are? And I have one slide, since I see this in here. I like to show you a bridge. We talk about bridges. A little bridge. See here, bridge? Have you seen this bridge in Ithaca? Science Center. You know where Science Center is? Route 13. And if you, so this is my bridge. This is Petropetrina Bridge. And it's a pedestrian bridge about 40 feet long, 8 feet wide. It's made of concrete, but the reinforcing bar are made of composite materials. And I invented that bar. I have a patent on a bar that has been used in here. So this bridge is reinforced with carbon fiber, reinforced polymer rebar. They call rebar for bars. So if you go by that bridge, you know that the guy talked to us on November 19th. Okay? That's all. Now, truss structures are some important structures and the most sophisticated structures we can design. Before I go to truss structure, I just review if we have a bar like this and we apply a force, how we call this bar? You have a bar and you apply force, tension. We call this tension bar, right? If we have a bar like this and we apply a force, we call this compression bar for what? in buildings, things that are vertical and are under compression are called what? Columns. Compression bars. Columns. If you take a bar and you support some supports, this is a symbol of a support, right? And this is the pin support to hold moving horizontal and vertical. And you apply a load in here. What we call this structure or that beam. They're beams, right? Now, if you have a structure that is like this, and I'm going to put some bars. And I support at this point and at this point. And we apply some loads. This is called truss. That's a truss. Now, when you do bending, this beam bends, right? The beam bends. And the bending of beam, the way this bends, right? This is a bend beam. Probably you have had a little background on that. The top fiber is under compression and the bottom under tension. Do you know that? When you bend something, right? Now, when you bend this truss, right, that will bend by straight bars, right? The top bar will be most likely under compression and the bottom bars will be under tension. Right? In a beam, if this beam is made to be optimized as a cross-section of the beam cross-section, the most optimum cross-section for the beam is like that shape, like an I shape. Have you had that? Or white flange is called, this is called webbed, and this is called flange. And when you bend the beam, the top flange is under compression and the bottom flange is under tension. And the web connects the top with the bottom, right? You have to connect somehow. So, in a truss, we have similarity to the beam because the top will be under compression, the bottom will be under tension, and these verticals and the diagonals will be like the web in that beam. This is the first time I'm teaching this lecture that way, right? Hilda's smart TA was my TA in 202. So he knows that I know this subject. So you tell what is this recording? That this guy is on top of the topic and good enough for that or what? So now, for the purpose of understanding structures, I would like to show how we can compute forces in a truss structure. When I say force in a truss structure, you can see this is made of many bars. They are called members, right? So, the truss structure. The basic is a triangular. If you take 3 bars and imagine that you have a pin in here, pin connection. Pin connection. What pin connection means? Can you tell me what pin connection means? When you have 2 bars and you connect them and you call pin connection. What's that mean?
Only connected at one point?
What do you say?
Are they only connected at one point?
Only connected at one point that can rotate. That's called pin connection. If you weld them, if you take 2 bars and you weld them one to the other at the end, they cannot rotate freely. But imagine that you have a bar in here. Let me do a little bit more. You have a bar, and you have another bar, and you have another bar. And if you put a hole in here, right? And if you put a hole in here, and if you put a hole in here, and you put a bolt or a pin, now you can see these are pin connected. But it's stable. If it's made of 3 bars, it's stable. If it's made of 4 bars, and you put a pin over there, and if you apply a force from here, this is going to collapse. It's going to do like that. Right? This is not a truss. How can you make that a truss? Okay. You just put another part. Now you make it a truss, right? And if I have this structure in here, I can have a triangle like that, and I can have a triangle like that, I can have a triangle like that. So I have 1, 2, 3 triangles, and I get a truss. Right? And I can make many, and I have a big truss, big in terms of many members. Right? But can be very small. But we can make trusses that are used in microchips, very little guys. Or we can make big trusses in a bridge, right? Or in space. Space structure is made of trusses. Now, why trusses and not beams? Beams are stable too.
Beams over a long span to much more as opposed to trusses, which keep its shape over a longer distance.
So beams has a limitation. How long can you make a beam? Because it's heavy. It's all material in here. If you make a truss, you take a lot of material out of this, and the truss is made of bars and can be lighter for the same to support the same load. So trusses can have much larger span than beam do. Also, what I'm showing here are trusses, 2D trusses. So trusses in one plane, but you can connect in the other direction and you get space trusses, right? When I was teaching some civil engineers, I used to take them it was a building where it's Albertine building where they play basketball over there, and they have some wonderful trusses designed about 15 years ago, were new trusses. And I like to just spend a minute and ask them to look up and see what a truss is. And that was good enough for a lecture, because if you want to do something, you have to open a book, study, and learn how to design trusses, right? So just you know what a truss is. This is 15% of your tuition for today. You pay tuition? Much tuition. You know, when I teach the course, I tell my students, I'm joking, right? I just say that if you don't like by the end of the semester what you learn, go to Dayton and ask for a rebate. I mean, for that course, you should get money back, right? That will be nice to have professors at Cornell. I'm talking to the guy. So, you already got something for your tuition today, that you heard about truss structures. So I'm going to show you how we can compute forces in truss members. Am I allowed to assign a homework? So you'll assign a little homework, you'll put on a web, and you'll be able to do that homework, and by doing the homework you are going to learn something, right? In this class you learn a little bit, but doing the homework you learn the real fact. Okay? Any question on truss structures? Many applications in civil, in mechanical, in many other fields you have trusses. They are light structures. They are the most modern structures. They are classical structures. They have been invented long time ago. They are in use. Most of the people look at the truss structure typically when they see a roof on a house, right? If you have a house and you build something, this is a house, right? And in here, you want to put a roof, it's a good idea to build something there like a truss, right? So this is a truss. You can give a little edge in here to create the eave, right? You build a shed. If someone driving on Three-Farmer Road, that exit from Eldo to Pyramid Mall, you do? You look up on the left-hand side after you go about 0.8 miles from the bridge, and you'll see a house. It's a white house, Mediterranean style. That's my house. I built that, I designed that house. And lately, I built a shed. When I say I build, I mean physically I work. Sometimes I have friends who help me, but now they're all done, so I work alone, right, when I have free time. I build a shed, and the shed, my shed it's a structure like this, and the truss has this kind of configuration. So I have in this area, you know, this is my truss. I give a little point in here to put some windows to give the impression that I give light somewhere else, to resemble the house, which has a kind of roof that is crooked a little bit. I wanted the shed to reflect the crookedness of the house. 906 Three-Farmer Road, right? So when you see that, you'll give a little respect more to someone who teaches you today, okay? Anyway, let me go to the basic of how we compute forces in truss members. How we compute forces in truss members. What we learned so far, that because the truss under these loads will bend like that, some members are under tension, some members are under compression, and these diagonals can be tension or compression. So let me do computation of determining force in truss member. And for the purpose of the level of intro to mechanical aerospace engineering, I would like to assume that we talk about statically determinate trusses. What means statically determinate trusses? You never heard about that, have you? You learn that in 2D, this is in plane structures, we have equilibrium equations which is in a system of forces x and y. If I put a structure in here, I can say that summation of fx should be 0, summation of fy should be 0, and summation of m with respect to a z-axis should be 0. You have 3 equations. Remember that? Have you seen this before? When you did the reaction for these beams, right? Do you understand this symbol for the beam? This is called a support, this is called a support. Typically when I make like this means roller can move horizontally. When I make like this means spin that is fixed in terms of displacement but can rotate, right? That the beam rotates. So we can compute, we have this equation and we have to find forces in this truss. So what are the, let's take a truss. So consider the truss. And I sketch a little truss in here. By the way, these trusses have names depending who made them first as a sketch or published something about. But that's irrelevant. So this is a truss. Let's assume that I put some forces in here at the top. I can have forces at the bottom if this truss is inside and you put pipes and you hang weights here, but for simplicity. And let's assume that I support this truss at this end and at this end. So instead of that guy, I put this system in here. And in some books you can see a little sketch like that, but this is called a roller. And this is called a beam. And you have forces. You heard about free body diagram? So free body diagram for that truss at this roller will be just a force like this. And at this pin will be a force and will be a force. So we have to give some names, right? So I prefer to give, let's say A, B, and I can go C, D, E, F, G, or I can say 1, 2, 3, whatever, right? And I give a name to this guy, and I would like to call this RA, and I give a name to this RB, and I give a name to this HB horizontal at B. So you have 3 support reactions. These are called support reactions, right? And how many members I have in here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 members, right? how many joints I have. Joints. 1, 2, 3, 4, 5, 6, 7. So we have 3 support reactions. We have 7 members. No, sorry, 11 members. And 7 joints or nodes. Now, the support reactions and this, in each member there is a force, tension or compression. Okay? So these guys are unknown. Unknowns, right? And we can write 3 equations for every location in a structure. But because we have pin here, the moment is always 0. So in fact we have only 2 equations per node. Right? 2. So a statically determinate structure is that satisfies the following criteria. R plus M equal 2 multiplied by number of joints. So this is number support reactions. So I have 3 plus 11 equal 2 by 7. 14 equal 14. If you meet this criterion, the truss is called statically determinate, right? So for example, if I have this truss, this is a truss. This is a statically determinate truss. But nobody stops me to put another bar. I put another diagonal. I make it better, right? This is statically indeterminate. In order to solve this, you need knowledge about what we have a little background in M&A 170. Understood? So we talk about statically determinate truss. Now, how we compute support reactions for this truss? How I compute RA? I put some forces over there, I want to compute RA, right? And RB and HB. Let's take the easiest one, HB. How I compute HB? I have these equations. If I say summation Fx equals 0, that all forces on a horizontal should be 0, can I see HB equals 0? So, I can compute from summation of Fx equals 0, result HB equals 0. From summation of M with respect to B equals 0. M at B. Imagine that you have a Z axis in here. This is X and Y. And Z is perpendicular, right? So I put the system in here. It's a Z perpendicular. I say M Z at B. But typically we say MB. But that means moment with respect to a Z-axis at B should be 0. I have RA multiplied by something, and I have this forces multiplied by the distance, right? That will result RA. Summation of m at z at a equals 0 to result rb. So I use fx, I use m twice, right? And I solve the problem. As far as support reaction, I can verify if I'm true, if I satisfy summation fy equals 0. So I take RA up, RB up positive, and this P1, P2, P3 negative, they should sum 0, right? That is how I compute support reaction. How I compute forces in this guy? There are two methods. You stop that clock a little bit, can you? No? It's raining outside. I don't want to go anywhere. Unless you want lunch or something. So, method of joints. So you take a joint, let's say joint A. Imagine that you can take a free body diagram of this guy, right? This is free body diagram. And you put the force in here that you computed before. RA. You take a system of coordinates in here, X and Y. You give name to this, AC. This is force, F in member AC. This is F in member AD. FAD. And this is a pin in here, right? And I can say summation, and this is alpha, that you know from the geometry of the truss, right? And I can say summation of Fy equals 0, right? Give me FAC sine alpha, will be cos, the other guy gets sine alpha, plus RA equals 0. And I find that FAC is negative, right? Which means, the way I put it here, I put like tension. If it's negative, means it's opposite, it's compression. See, this theory gives me the sign in a bar, right? So I find FAC equal minus RA over sine alpha. If RA was up, which is positive along the Y, this would be negative. This negative means compression. Once I have FAC, I can compute FAD. From summation of Fx equals 0, I have FAC cos alpha plus FAD equals 0. Solve for FAD and gets plus. Because this is negative, gets plus, which means tension. That is how we solve a truss, right? So let me do some numbers quick, so you guys, you learn something from me. So I have one example. Lucky I was told, so I put my notes from some years ago when I teach architects. Architects like truss structures. You know, you have a school of architecture at Cornell. Most often the best in the world. You do know that? I teach structures. Those guys, they don't like to hear about vectors. They don't know how to compute alpha. When you say cos alpha, it's trouble. You have to explain what that means, right? But otherwise, they like trusses. So, example. The example I have, it's a truss like this. It's 3 meters here, 3 meters. It's a support at this point A, this is B, this is C, and this is D. And I apply a force of 600 Newton and a force of 400 Newtons. And this dimension is 4 meters. And the truss is supported at C by a P. So this is roller, and this is P. You see, truss can be different than the simplest truss that I put first on the board, right? And what we like to do is to compute support reactions and to compute forces in each member, and also tell if it's tension or compression. Understood the question? So, determine reactions, member forces, and tell tension or compression. If we do that, someone can design that truss, because now you know if you have a force, how much material you have to put over there to resist that force, right? And you know how to do tension members. Probably you don't know compression members. But that's the problem we have to do. First step, member forces. We need a free body diagram, right? So free body diagram. I will re-sketch this structure, and because I'm a little bit in rush, you do sketch again. Take it here and put here RA. Take this support in here and put here two forces, right? And I call those forces CY and CX. And in some books, instead of RA, I prefer to call this AY. Now that tells me that there are forces along Y and along X. It's a good practice, understood? So my system of coordinates in here is this, X and Y. And this, it's a free system. I can move at any location where I can put the structure in my system, right? That means the Cartesian system in 2D. So let me compute those reactions. So I'm going to do some numbers. So from summation of MC equals 0, I take moment with respect to C. I do intentionally that because at C, I have these two forces which I do not know, right? So I take moment with an axis in here. So it will be what? AY AY multiplied by 6 meters, right? That will rotate this structure clockwise. So I assume clockwise positive, like that, right? This 4 will rotate like that, this will rotate like that, you see? So I have to make distinction, forces that rotate one way and forces the other way. So I do positive for clockwise, and this will be minus 400 multiplied by 3 meters, and minus 600 multiplied by 4 meters. And this should be 0. And from that I have A along Y equal to 600 newtons. Now I can use other equation like summation of Fx equals 0 or summation of Fy equals 0, and from this I'm going to get Cx, and from this I'm going to get Cy, and the numbers are Cx minus 600 newtons and Cy equal minus 200 newtons. Now I like to compute some forces and some members. And I like to use the method of joint, right? So let's take the free body diagram of joint A. So free body diagram for node A, right? So I have a force in here, a force member, and I put this reaction, which now is known. I put 600 newtons, and I call this FAD, and I call this FAB, right? And I call this alpha, and I see that alpha equal the inverse of 4 over 3, which is 53.13 degree. That's alpha, right? And I can take summation of Fx equals 0, right? And I will have FAB cos alpha plus FAD equals 0, equation 1. I take summation of Fy equals 0, and I have FAB sine alpha plus 600 equals 0, equation 2, and I solve 1 and 2, and I get FAB equal minus 750 newtons, and FAD equal 450 newtons. That's the solution. And about sine, what sine? What? This negative says compression. And now, after I solve this joint, I can go to another joint. You see, I could not start at B. Because at B, if I have started at B, I have 1, 2, 3 unknown forces, and I have only 2 equations. So I have to start with a joint that has only 2 unknowns. But once I solve this, I can go to B or to D. D, and I can do the other members. So if I go to next three-body diagram for joint B, I just take and I put the force in here, 400 newtons, and this guy, let me put it in red, this guy was FAB, this is minus 750 newtons. And again, I do equilibrium of that node. Imagine that I have X and Y. I do equilibrium and I solve for FBD and FBC. So you go from joint to joint. There is a simpler method called also method of sections. Method of sections. If I have a truss like this, I can cut the truss in here, and I can have a three-body diagram. And I have a force in here. And I take the equilibrium of this guy, and I can solve the problem. And I don't have to solve this joint, that joint, that joint to get in here. I can go anywhere in a truss. That you'll see in the 202. Thank you and good luck.